Alright, hi everyone, welcome to my YouTube channel, City of Elections. And in this video we're talking about partial fraction expansion. So, of course, partial fraction expansion is a mathematical technique. It's a technique and it's used in mathematics. Okay, used to do what? Decompose a rational fraction into a sum of similar fractions. Now, we said in the previous video, or some videos before this, when we say rational fraction, okay, rational fraction. Now, this rational fraction, in order to reduce it to sum of simpler fraction, we need partial fraction decomposition. Okay, we need partial fraction technique. Now, let's work with this. Say let x of s be a strictly proper rational function. Okay, rational function which has n poles. Of course, poles are the numerator, roots of the numerator. And then suppose all poles are distinct, there exists complex number ci such that s of s can be represented as this. See, all this statement, all that has been said there is just that you see this, whatever you have on top here, okay, whatever you have on top here, you decompose it to c1, c2, cn. Okay, and then for our roots, for what we have in our roots, we are going to have it as this root will be in the first place, second root will be in the second place, and so third root just like that. Okay, when I say third root, I mean like pole 1, pole 2, and so on. Okay, when we work an example with this, you will understand what we are trying to say. Okay, then the second thing is that suppose the rational function has distinct poles, but say p1 is repeated arrow times. That is, if you have pole p1 2 times, you have p1 2 times, what you have to do is this kind of expression. Okay, so you have ds, and instead of having c1, c2, c to cn, we'll have d1, d2 to d arrow to the number of repetition. Okay, because look at this here, s minus p1 is repeated. Okay, so the number of repetition will continue until like p1 again, second time, p1 again, until the number of times p1 is squared. Okay, while we have this numerator repeated until the number of times p1 is repeated before you now go to c2. While for the case where we do not have a root that is repeated, we'll just have c1, c2, cn, and so on, p1, p2 to pn. Okay, so note that c and d are constants. They are called residue of the function s of s, and that's because they are called residue because they are constants. Okay, they are called residue because after, when we decompose the function, what is left, like what is left, so that's why we have as a constant. Okay, so instead of calling a residue, you can just say they are constants. Alright, so but don't just take it easy, okay, because what I'm trying to talk about, what are we seeing here, when we work an example with it, it will be clear what we mean. Okay, now this knowledge we are going to apply it right here in electrical network. Now looking at this electrical network, what are we actually doing? Now look, for the ROC network, why is it ROC network? Because we have resistor and capacitor. So we are going to, from what we've learned so far, differential equation with Laplace transform, system representation, partial fraction expansion, what I just explained will be made very clear in this example here. Okay, so all we've learned so far, we're going to apply them. Most of the things we learned, we're going to apply them here. Okay, so now what's happening here? We want to analyze this network. We want to analyze what? This network in order to determine the output signal y of t. X of t is the input signal. Exactly. X of t is the input. Y of t is the output signal. So to determine this output signal, look at this last step here. Okay. Now to determine this output signal, or to put it simply, let us first derive or let us represent this system using differential equations. Okay, are we ready? So when we represent the system using differential equation, we can then derive the or easily get the output signal. So let's go. So for the RLC network above, V equals IR. This is obvious from Ohm's law. I of t equals what? Change in voltage over change in current multiplied by the capacitance. Okay, so current, the current through this capacitor, okay, current through the capacitor, we can represent that saying I of t, it changes with time, okay, as a function of time, I of t. Okay, you can say it is the capacitance C multiplied by change in voltage over change in time. Okay, now since we've said that I of t is what? Change in voltage over change in time. Voltage here, what is the voltage through this guy? The voltage through this point, y of t. So we are going to put y of, where we have V, we are going to put what? Y of t. Are we seeing it? Of course, dt remains under dt. And this expression can be written as C is C. This differentiation is in the first order because it's let me put this here. For second order, we have this now. You have 2 on top. Sorry. We have this. This for second order. So first order, there's an invisible one here. So since it's first order, to write it as y of t, just put 1 dot there because it's first order. Okay? All together. So the next thing now is to say y of t equals what? All this. How do we get this? This is the y of t we have, right? You just bring it here. Now the current equals what? From Ohm's law, current V equals IR, right? If you make I so this formula, this guy goes off. So I equals V over R, and the voltage, output voltage, the arrow, of course, this is the arrow here, which is this one. Then the voltage at this point, is what? This is for the source voltage, right? So this X of t comes in, there will be a voltage drop here. So when there is a voltage drop here, that voltage drop, when there is a voltage drop here, what will be left at this point? Okay, minus y of t. This what will be left at this point, because this voltage across this the voltage drop here, meaning what will be left is this guy here minus this. That's what will be left. Okay, so S of t minus y of t, that's what we're going to have here. S of t minus y of t. Okay, so from this point, of course, you can separate this is the LCM, so you can separate this over this, as we have here, minus this over this, so we get this. Now we can simply bring this y term cross to the other side, so you now have y dot t plus y of t over RC equals S of t RC. So you now have all the y terms here, which is outputs, and then x terms here, which is inputs. Okay, So now we just derive the simple differential equation from it, saying this is the differential equation that represents the system or the network above. Now we can derive the transfer function of the system by simply using the impedance representation. Using the impedance representation, what do we mean? R, of course, is R. Capacitance in impedance representation is what? 1 over j omega c. The 1 over c. And of course, the j omega is s. So that's why we have this. Okay? And then all the time domain will turn into s. So here will be x of s, here will be y of s. Okay? And then using voltage divider rule to calculate the voltage at this point, from voltage divider rule, which is this Vn equals Vs Rn minus Rs, meaning the voltage at that particular point n we are looking for, voltage at that point is equal to the resistance at that point, same point, multiplied by the source voltage divided by the sum of all the resistance. So what is the voltage at that point? Y of s. Have it here, Y of s. What is the total voltage, source voltage? X of s. What is the resistance at that point? 1 over sc. All over rs. That is the sum of all resistance. So all the resistance we have this. So this plus this. So there we have this plus this equal to this is the transfer function. Okay? So we can just do our answer like this. So of course you can, if you want to say y of s equals 1 over sc over x of s over r plus 1 over sc. You can do it this way if you want. But you can just give your answer like this. So we have gotten the differential equation of the network above, and we have also expressed the transfer function successfully. If we had some figures here, we would have taken the Laplace transform and then partial differentiation and partial fraction decomposition. Okay, but we just stop here for now and let that be. Okay, alright. So in the next video we are going to work this example, and in this example we are going to apply the partial fraction decomposition. Yes, we did that here. Beautiful. So this will be in the next video. So I'll see you in the next video. Thanks for watching, and bye for now.